So in the previous session, we have discussed three definitions taken from three different sections. And now I'm going to do one or two problems taken from the exercise of section 2.4. So one problem which I'm selecting is question number 14. And it is given as follows. Let capital V is equal to a vector space containing matrices of the form where A, B, C belonging to F. Question is construct an isomorphism from V to F3. Construct an isomorphism from V to F3. Probably you have understood by looking at this particular problem, probably you have understood why I drew that diagram. Okay, let us draw the diagram for the sake of your understanding. Once again, quickly, by construction actually we mean that if we have two vector spaces, this is capital T, this is Fn, this is Fm. Okay, this is the basis is beta, here basis is gamma, and since they have talked about single vector space V, not two vector spaces, so you can consider probably they have asked you to find a transformation like phi beta or phi gamma, and that is your LA from Fn to Fn, Fn to Fm. So that is the diagram. That is the diagram we actually drew in the previous session. So if you cannot recall the definition, or if you do not understand the diagram, you will not be able to understand what do we mean by construction. Okay, so now as we are familiar with the definition, so let us try to solve it. The element of V is of the form A plus B 0 C, which can be expressed as follows. Now you see V contains 2 by 2 matrices, and its basis contains the following elements. What are these elements? E11, E12, E21, E22. So what are these actually? 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Okay, and you see, if you consider this element A plus B 0 and C, you can express this element with respect to these basis elements. So we can write it as A into 1 0 0 0. Then A plus B can be written as A plus B. This can be written as A plus B into 0 1 0 0, and we have 0 into 0 0 1 0. But this is there is no logic in writing it, because we are dealing with F3, and here the term is always 0. It is fixed. it is 0. Okay, so if you multiply this basis element by the scalar quantity, if you multiply this basis element by this scalar quantity, so it is actually not, it will actually not what? Will not be effective. Okay, why not effective? Let me tell you. Let us keep it over here. If you can ask me that, sir, what is the problem if I keep this 0 0 1 0? So for the time being, let us keep this particular thing because it is in the basis element. But what is the problem? Because you are constructing something, what will be the problem? We will be understanding once I finish this problem. So we are keeping it 0 0 1 0. And lastly, you can write it as C into 0 0 0 1. Okay, now this is the thing. Okay, we have expressed, you multiply all all these matrices by these scalar quantities and add, you will get the same thing. Now what is x beta? If you have seen my previous videos on linear transformation problems and on the problems which I discussed on the basis of section 2.3 of Friedberg, you have known that how to find this x beta. X is the vector. Here my vector is a vector space is V. Here my vector space is V, and x is actually the element of the form a plus b, 0 and c. This matrix is the element of the vector space, is belonging to the vector space V. So I'm writing on the next page. Okay, probably you have copied it. So I'm writing in the next page that, so in that case, your x beta is my this basis. I'm calling this basis as beta. Let us name it as beta. So this x beta will be nothing but this element a plus b, 0 and c. This is my element. Put it inside a third bracket. This is not a matrix sign, remember, with respect to beta. And that would be the column vector. That would be the column vector a plus b, 0 c. a plus b, 0 c. Now we know that this column vector of this form actually belongs to F4. You know this very well from our today's previous discussions. But this cannot be true with respect to the current problem, because in the current problem you are going to construct a vectors, an isomorphism from V to F3, and F3 contains 3 rows, 1 column and 3 rows. So therefore we cannot consider this particular matrix with respect to the condition of the problem given. But why it is happening? It is happening because we considered unnecessarily this. Okay, so that's why I told you that, okay, let us consider it, but you will get to see why I'm not going to consider this particular basis element. Okay, so let us write it in a proper way. So this would be just C into 0 0 0 1. Okay, this is actually not required with respect to this construction, and therefore this element will not be there. And then immediately we can write that, yeah, this column vector actually belongs to F3. So this is the construction which we have made. This is the construction which we have actually made from V to F3. And you know, not only this, you know from the definition which I wrote in my previous session, that your x beta is actually phi of beta of the vector x. So actually we have constructed a mapping phi beta from the vector space V, which is given in the question, to F3. And that is the mapping. This is the mapping. So we have constructed a mapping by phi of beta x as a plus b and c, where x is a plus b, 0 and c. So that is your answer. So you will not understand the logic which is presented over here if you do not understand the diagram. You will not be understanding the diagram if you do not go through the definitions. One another problem I'm going to do in my today's class, and with that particular problem I'm going to end my today's session. It is already 8:32 and I know that you cannot take any more, but this definition, this is the last problem which I'm going to consider in today's class. So let me write the question, and I am choosing the question from the section 2.4 exercise, question number 19. Question number 19 I'm considering. So for this question, I'm going to a fresh page. Exercise number 19. The question is written. It is taken from Friedberg's linear algebra, section 2.4, edition, 4th edition. Okay. And the question is given as, in example 5 of section 2.1, I am copying the question as it is given in the book. Section 2.1 means the section 2.1 of the Friedberg book. Example 5 is written over there. The mapping T colon M2 cross 2R is defined from a mapping T is defined from the on the vector space M2 cross 2R, defined by T of M. If you choose any matrix M from this matrix M is a 2 by 2 matrix, we have to take its transpose for each M belonging to M2 cross 2R is a linear transformation. We don't have to prove that it is a linear transformation because it has already been defined in section 2.1 of the book. Let beta be the basis, E11, E12. You know very well that what does this mean. We have just now used it in my previous problem. Which is a basis for M2 cross 2R, okay, as noted. Question is, we have to compute capital T beta, and number B, verify that LA phi beta M is equal to phi beta T into M for A is equal to capital T of beta and M is equal to 1, 2, 3, 4. Now the student who has attended my previous sessions very carefully and my previous classes and have gone through the books and have gone through the YouTube videos, they are going to understand the problem. And those who have actually cheated themselves by not studying, okay, so they are not going to understand a single line of what I am doing, and the entire question will be to him Hebrew-like of things. Okay, so I'm going to solve the problem in front of you. Problem is important from the perspective of the understanding of the logic, but it is not a complicated problem. Now you see that this mapping is given, this linear transformation is given in front of you, and this is the vector space of all 2 by 2 matrices. We are choosing an element M from this vector space, and transformation is defined in the following manner. So if T is applied on the matrix, we have to consider its transpose. So we have to write the matrix representation of this linear transformation. We have done lots of problems of similar types. So first of all, if you can recall, we have to choose these basis elements. So first basis elements we are choosing, and if I apply T on it, we have to take its transpose, and that would be same as the matrix itself because it is actually a symmetric matrix, and it can be written as this, as a linear combination of the basis elements as I am writing. Let us do the same thing for the other elements. Okay, so let us quietly do it first of all. You also quickly copy this because I am going to go to the next page very soon. I'm not explaining this because it has already been explained several times. So probably you are understanding. And if you are not understanding, then it is your problem. It means that you have not studied at home. It would be a nice practice if you are not copying and doing it by yourself. Okay, so we have got the scalars. I'm marking the scalars over here. So these are the scalars we have got. Just check if you are doing it by yourself, just check whether you have got the same set of scalars or not. And now on the next page, I'm going to write the matrix representation of T with respect to the basis beta. Beta is given, beta is defined over here. So your T beta, T of beta is actually becoming, we have to consider the scalars column wise. We take the transpose actually, transpose kind of thing. So it becomes 1 0 0 0 0 0 1 0 0 1 0 0 0 0 0 1. Just check it. Okay, just check that we have got the same thing. Now this portion is done. I'm coming to the next portion. Verify that this is true. Verify that this is true. Now, if you have understood the definitions of LA, phi beta, etc., then you are going to understand everything. And my capital A is actually this matrix. The LA function which is being constructed over here is with respect to the matrix capital A, and M, the matrix on which capital T is being applied, is the matrix given as 1 2 3 4. So we are going to verify. Verify means what? We are going, if I consider this part as left hand side and this part as right hand side, we are going to check whether left hand side is indeed equal to right hand side or not. Okay. So let us, this is our part 1. Let us solve part 2. Okay. So take the matrix M from M2 cross to R and the matrix is given as 1 2 3 4, because it is a 2 by 2 matrix. 1 2 3 4. First we are going to calculate which part? First we are going to calculate this phi beta m. First we are going to calculate this phi beta m, and from our previous, that is the definition of phi beta x. Try to recall, that is the definition of phi beta x. So with respect to this definition, phi beta m, we are going to construct, that would be what? That would be m of beta, m with respect to beta. Now what is beta over here? Beta is given to be E11, E12, E21, E22. This is your beta. I can express this 2 by 2 matrix with respect to these basis elements as follows. I can write it as 1 into E11, 2 into E12, 3 into E21, 4 into E22. What does it mean? It means 1 into 1 0 0 0, 2 into 0 1 0 0, 3 into 0 0 1 0, and 4 into 0 0 0 1. Now when we write this function phi on m, we apply this function phi on m with respect to beta, that becomes actually the matrix representation, and it is similar to the matrix 1 2 3 4 taken column wise. So that is actually what this is. Actually we have calculated phi beta m. Now what is left hand side? On the left hand side, I'm going to apply LA. I'm going to apply LA on this matrix phi beta m. So let us do it. So let us now write LHS. On LHS, we have LA applied on phi beta m. So that is LA applied on m beta. That means LA applied on 1, 2, 3, 4. And that is what we are going to multiply 1, 2, 3, 4, which is a 4 by 1 matrix with a matrix capital A, which is, according to the question, is T beta. So we are going to multiply this by T beta from the left hand side. So 1, 2, 3, 4. And what is T beta? T beta is a 4 by 4 matrix. So we are writing it over here. 1 0 0 0 0 0 1 0 0 1 0 0 0 0 0 1 multiplied by 1 2 3 4, and the resultant matrix would be 1 into 1 plus 0 into 2 plus 0 into 3 plus 0 into 4, that is 1. 0 into 1 plus 0 into 2 plus 1 into 3, that is 3. That is 3. And 0 into 1 plus 1 into 2 plus 0 into 3 plus 0 into 4, that is 2. And lastly 4, 1 3 2 4. So LA phi beta m has been written as 1 3 2 4. Okay. And just a minute. Okay. So that is obtained. And lastly, we are going to write RHS. RHS, what is RHS? RHS is given to be phi beta of Tm. Phi beta of Tm. So that is equal to phi beta of Tm, which is actually the Tm, the matrix representation of Tm with respect to beta. What is Tm? Okay, let us check it. T is my transformation from V to, no, from, not from V. T is the transformation taken from M2 cross 2R to M2 cross 2R. Okay, and T is when we choose an element M from M cross 2 R, 2 cross 2R, then it becomes the transpose. That is your T. Now here in this case, your M is 1, 2, 3, 4. Okay, and Tm, this is actually what? T of 1, 2, 3, 4. That is by definition 1, 2, 3, 4 and its transpose. And that is 1, 2, 3, 4. Okay, so we have calculated Tm. Now, if I apply now this matrix 1, 3, 2, 4 can be written with respect to the basis as follows: 1 into 0, 0, 0, 0, 3 into 0, 1, 0, 0, 2 into 0, 0, 1, 0, 4 into 0, 0, 0, 1. Okay, and this is the matrix element. This is your, actually this is your X. So X beta, if I consider X beta, this is actually what? 1, 3, 2, 4 written with respect to beta, or you can say that is nothing but your Tm with respect to beta. So by definition, what is Tm beta? Tm beta is the column matrix 1, 3, 2, 4. And you see, in the previous case also we got 1, 3, 2, 4. So actually this is La of phi beta of M. Okay, and that is nothing but your LHS. So the result is verified. LHS equal to RHS. So hope you have understood this particular thing which I have written over here. Let me draw a boundary so that you can understand properly. Okay, this is not a rough work which I've done. This is extra work done on the side of the page. The result has been implemented over here. So that thing is connected to this thing. Okay, so I'm opening the chat box so that you can write your student IDs over there. So now you can write your student IDs, and this completes my problem. This completes my problem of the question number 19. Okay, this completes the problem question number 19. And I must say one thing, I must tell you one thing with my today's discussion, I have actually completed officially discussing the module 4 with you. I'm no longer to discuss module 4 any long. I am not going to discuss any further about the topics of module 4 officially with you. Unofficially, you can ask me any questions anytime, but official discussion is closed over here. By today's discussion, I am actually putting curtains down to the module 4. Okay, although many things are still remain for you to study, I have leaving many problems for you. Only I know very well that only interested candidates we are going to solve those problems or going to think over those problems. Maybe he cannot solve it, but he is going to think over that problem. He or she is going to think over that problem. From next week onwards, I'm going to start discussing module 3 with you. And as I have decided that from next week onwards, I'm going to discuss module 2 with section B and module 3 with section A, so that I can cover the two topics simultaneously. Otherwise, I shall not be able to finish the syllabus. But that doesn't mean that since I'll be teaching module 3, so in CA2 you will be only giving the module 3. You have to answer module 3 questions only. It is not like that. In CA3, you are going to write both the answers for module 3 as well as module 2. You are going to attend direct one-to-one session with me with respect to module 3, but you have to watch the video uploaded in YouTube, which will be taken on the basis of module 2 with CSE section B, and CSE section B is going to do the reverse opposite to that. So the CA2 examination which will be conducted, will be based upon module 2 and module 3 of the syllabus for both the sections. From next week onwards, CSE A is going to attend module 3 directly and will be seeing the video of module 2 in YouTube. And CSE B is going to attend module 2 directly and going to watch module 3 in YouTube. So that is the structure I'm going to follow. Okay, I hope that you shall be agreeing with that. But also it is you are going to you can ask me questions from either of these two modules at any point of time. And one more thing, before I finish my today's session, I want to say one thing that I did while putting problems in the CA1 examination. I gave you a problem that W is containing the functions polynomials of PF, where fx equal to 0 or fx has degree n. Okay, so I asked you n greater than or equal to 1. I asked you whether it is which of the following statements is incorrect, and I gave you choices like W is not a subspace of PF. Okay, W is not a subspace of PF. Most of you have ticked this particular option, which is incorrect, which is incorrect in the sense that it is actually not a subspace of PF. But I asked you which of the options is incorrect. So it is not a correct option for the questions. In the question, I am going to look for the incorrect option, but it is actually true. W is actually not a subspace of PF. So it is not incorrect. The statement is not incorrect, and therefore this should not be true. But in the option number B, I put the W is closed with respect to is not closed with respect to scalar multiplication. By mistake, I did this, and therefore this particular option is actually not incorrect option, because indeed W is closed with respect to scalar multiplication. But W is not a subspace of PF is because W is not actually closed with respect to vector addition. Why it is so? Let us consider two polynomials like this. One polynomial is of the form and another polynomial of the form minus xn plus xn minus 1 plus 1. Okay, two polynomials I have considered. This polynomial is having degree n, it is in W, and this polynomial is in degree is of degree n, it is also in W. Now if I add these two polynomials f1x plus f2x, you will see that these two items will cancel each other, and you will get a polynomial of the following form, okay, which is not of degree n, and therefore f1x plus f2x does not belong to W. Therefore W is not closed. Okay, W is not closed. This is the reason for which W is not a closed, and therefore W is not a subspace. Okay, so this should be the correct option. This is the incorrect statement. So with this, I'm going to conclude my today's session. Hope to see you next week. The time will be told to you later on through CR. Till then, best of luck with the module 4. I hope that you will be all trying problems from the book. Okay, so good night and see you soon.